So for today's lesson, we're going to be covering something called shortest path algorithms. So last week, before the break, we covered breadth first search and depth first search. And these algorithms were a great stepping stone into discussing algorithms, as well as, with graph theory, discussing graph theory algorithms. But today we'll be discussing shortest path algorithms. So, and the questions that I've taken up, the questions that I presented, as well as an example that I showed in BFS and DFS, you might be wondering why you can't just use BFS from the example I showed you earlier in regards to, finding the shortest path. Now, with that example that I handled was unweighted graphs. So that looks at each graph having no associated weight with it, and that each edge is going to be exactly the same. So we can just assume that, okay, if we go one step at a time, we'll always find the shortest path. We'll find the shortest path first. In this case, we can't use that same mentality since each edge is now going to be a different weight. So, if we start with a weight of one weight's going to be, a weight of 3 or whatever, and another weight's going to be 5 or weight of 8. If we add just edges like that willy-nilly, then we won't find the shortest path. We'll find another different path. Now, before we start discussing these algorithms, we have to start just talking a bit more about like the different designs of algorithms. So we called them the algorithm design paradigms. This is what the word is, paradigm. And understanding the different designs of algorithms is pretty important. We can use to like design algorithms that can not only solve our problems, but it can also solve it in the most efficient manner that will be able to pass the memory and time constraints. So here are the common algorithm designs you'll encounter. So the first one that we've been covering so far is brute force, and this is pretty much when you attack the question in every way possible. You don't care, just going at it. And it takes the least amount of brain power to think of, and you can just jump straight ahead. For simple questions, this gets the job done, and you're on your merry way. However, once you get into more complex questions with complex solutions, the time and memory complexity can go out the window. All right. So it's much preferable for simple questions. It's really preferable for much simpler questions. But you should avoid for questions such as the Junior 4 or Junior 5 on the CCC. So whoops, I forgot to share this lesson with you guys. Let me get you guys up with this lesson. So Junior 4, Junior Week 11, shortest path algorithms. All right, and I posted that in the chat, so you guys can easily follow along with this week's lesson if you guys want to that way, or you can just continue watching my stream. All right. So it's much preferable just for simpler questions. But you should start avoiding brute forcing in Junior 4, Junior 5 if you want on the CCC if you want to completely solve the question and get all the points. You can still get partial points if you brute force these questions, but for the full intended solution, you'll need to look past brute forcing. The second algorithm design paradigm that we'll be looking at is divide and conquer, and this goes back to an old saying that goes, the start of a journey of 1,000 miles begins with a single step. And likewise, rather than trying to attack the whole question, we can break down this question into smaller questions that you can easily solve. And this is great. This will greatly help you where you don't have to overthink what the question is, as well as increase your efficiency. Why try to attack the question when you can just attack the smaller bits of the question to understand the bigger picture? All right. Greedy algorithms, greedy programming. So Why think ahead? Why think of the big picture and think ahead? Think small and just find an optimal path that you're already currently presented with. You'll be bound to find the most optimal solution. Maybe. And actually, no, you won't be able to find the most optimal solution. And because with greedy algorithms, you just take the most optimal path that you know so far. Denoting the greedy part of the name. Let's say I give you like each step of the way. Okay, you can choose this path of $5 or this path of $1. Of course, everyone's going to choose a $5 path. That's more money. I'm greedy, and this $5 path will go. Okay, you want to take a path of $7 to $100. Everyone wants to take the $100 path. And that's the same idea. But if you took it slowly and found the whole picture, you might have ended up with a better solution. So in this GIF here. It starts off 7, and you have the path. It splits between 12 and 3. And the greedy algorithm will be like, okay, I want the biggest number. So you choose 12, and then in this case, it splits off to 5 and 6. Oh, I want the biggest number. Choose a 6. But the actual largest path would you would actually have taken 3 and taken 99. All right, and that's the idea of greedy programming. If you're trying to be greedy with all the information you know of so far. And then the last paradigm we'll look at next week is this dynamic programming. So let's say you're constantly solving the same question over and over again. I'll take, for example, I keep throwing indexes of the Fibonacci sequence, and I keep demanding the answer. This will get boring and repetitive if you guys brute force it, you guys are looking at it, you guys are solving it every single time, And you realize for Fibonacci, you look at the previous 2 indexes, of course. And with dynamic programming, we can break down the questions into smaller overlapping subproblems that we can, store and retrieve later. And this will greatly increase efficiency as you have to only solve the problem once rather than solving it a billion times. Why solve, Fibonacci, fib at 5? Let's say I give you fib at 5, then I give you fib at 6, then I give you fib at 7, fib at 8, fib at 9, fib at 10. Once you've solved fib at 5, you can solve fib at 6. Well, so you can just easily keep track of the fib at 5 part than the fib at 6, As opposed to with fib at 6, you're solving everything else. If I give you fib at 10, since you already know fib at 5, fib at 6, you can easily solve everything. Why do I do it a billion times? All right, and that's the idea of dynamic programming. And those are the paradigms. Those are the algorithm design paradigms that we're looking at. All right, and now we'll actually introduce shortest path algorithms. All right, so prior to diving into shortest path algorithms, I'll need to explain a few things. So as I stated earlier, we'll be covering weighted graphs, unlike in previous questions where we were only covering unweighted graphs. And for those who are confused, let's say we have a map of the city, and we want to take the shortest path from one end to the other of the city. If we were looking at an unweighted graph, it looked like every road on the map is completely equal to each other, with the same distance from one point to the other. When in fact, that is not the case. Roads have different qualities, have different, different distances between each other, and so on and so forth. And a weighted graph would show that each road on this map has a certain distance from one to the other, and as such, we can look at the shortest distance from one location to the other. Because if we're looking at an unweighted graph of of the city, and we want to go from one location to another, it will give you the least amount of road to take, but it won't tell you the shortest distance. And there are 2 other concepts that I need to explain to briefly explain. First is the concept of relaxation. So in terms of shortest path algorithms, relaxation is if we find a shorter distance, the algorithm will replace the shortest path value to cut down on the other cases. So if we already find a shorter path, then we can to a certain location we can cut down on the other cases. And once we also find the shortest path to a certain location, then every path that leads from that location will just adjust to that shortest path from that location. All right, we don't have to fiddle around with values and such. And secondly, the shortest path from a location to itself is always 0. There's nothing contradicts that. If we start a location, you're already there, so it's a distance of 0. How much energy does it take for you? Let's say you're sitting down right now at your computer, looking at this, this lesson. What's the energy? What's the distance it takes for you to be at the same location you are? 0, right? You don't have to get up, walk around, then sit back down. No, that'd just be a waste of energy and a waste of like time. Instead, you're already at this location. Just stay in the same place. You took 0 distance to get to this location. Now, two algorithms that we'll primarily be looking at are Bellman-Ford and Dijkstra. So this is a Dutch name. So it's Dijkstra, and it's pronounced Dijkstra. These algorithms look at the shortest path between 2 points on a weighted graph. This means it only looks like we're looking at a starting position and we're finding a path to an ending position. That's it. We'll also cover one more algorithm that's less important, but pretty interesting nonetheless, and it's called floyd-warshall. Rather than looking specifically at a specific starting location and a specific ending position, it tells you all the shortest paths from every position to every other position on the graph. And this gives the name of an all pairs shortest path, where it gives you the shortest path between every pair of vertices on a graph. And there are more algorithms out there, but we'll primarily look at these 3. Even then, you'll just be fine just using Dijkstra and the CCC. However, learning all 3 will be very useful if you want to do some more advanced problems in the future, especially if you plan on going to CS Club Senior in the future. They'll probably cover Bellman-Ford and Floyd-Warshall more in depth, but for now, we'll cover these 3. All right. So Dijkstras algorithm, it's named after a person who named it, Edgar W. Dijkstra. He's a Dutch guy. Is a greedy shortest path finding algorithm that finds the shortest path between nodes in a weighted graph with non-weighted weights. So this pretty much means, okay, it's a greedy algorithm, so it wants to always take the shortest path no matter what. It's lazy, it's like us. We don't want to do all the work. We want to take the shortest route. And as such, Dijkstra's algorithm always takes the shortest route and such. And it finds the shortest path between nodes in a weighted graph with non-negative weight. Non-negative. It should be non-negative. Non-negative weights. All right. So that means you cannot have any weight that's less than 0. And you will break Dijkstra's algorithm if you have a non-negative weight. As a greedy algorithm, it chooses the path with the lowest weight at every point and keeps track of the currently known shortest path from each node to the start node, updating it once it finds the shortest path. This process continues until the shortest path to find every node between the start and the destination is found. Now, before we actually dive into implementing Dijkstra's algorithm, we need to discuss something called a priority queue. Now, like we discussed in the last lesson, we discussed the queues and stacks. And to actually implement Dijkstra, though, we need to use something called a priority queue. So a priority queue is very similar to a queue, but not at the same time. You guys might be confused. And if you guys are confused, feel free to let me know. But I'll briefly explain now. So we can take from the priority queue, similar to a queue. However, rather than taking it in an orally fashion, like a queue, so like if a queue where like you line up first come first serve, we can take from a queue, of course, but instead, rather than having it first come first serve, we assign the priorities in each of the items in the queue, and those of higher priority get served first. So the best example is a hospital triage system where it doesn't matter when you arrive at the hospital, the people who arrive in the most critical condition are assigned a higher priority and are served first. So let's say you arrive at 8 a.m. with just a headache or a cough, and another patient that is having a heart attack arrives at 10 a.m. Who goes first? In this case, the patient with the heart attack is given a higher priority over you with just a headache, and will go first over you because a heart attack is a critical condition, as opposed to you just having a cough and a headache. That's lower. That's a lower priority. So it's not first come first serve anymore. It's now a priority based system. And to implement a priority queue, it's very similar to implementing a queue. So all you do is import queue, and instead of doing queue.queue, you do queue.priority queue. And then you still put the same way, and instead it should give you all the values in order of priority. So if I put 1000, then 1, then 10 into a priority queue, what I should get out is 1, then 10, then 1000. So by default in with queues in Python, it should give you the lower numbers are given a higher priority. All right. Is anyone confused about that? Does anyone have questions about that? If not, then I'll proceed. All right, so implementing Dijkstras algorithm, it's very similar to BFS in which we need to know which vertices are adjacent to each other, as well as what vertices to search for with using a priority queue. However, what's different is that we need to keep track of the total weight of the path from the starting vertex to any given vertex. So in this case, so I have this notation here. So first, we start with the distance, all right? So the distance for each vertex from the start to some end, I guess, from this from the start to the end of any vertex, it's going to be some arbitrarily large number. It doesn't necessarily have to be this number here. It just has to be has to be larger than the maximum weight of a path, you know? So that's the given. That this keep tracks of that distance, and the distance from the start to the start is always 0. So we have to set the distance from this start to 0. And then now we first create the priority queue, and we add the distance that we're keeping track of, and of our path from the start, and the node we're searching for. And note that we have to put the distance first. Add a priority queue will first check the first value given in the priority queue. So if we're given this pair here, it will first rank each thing in priority with this first value here. All right, and then it does the normal thing with BFS and such. So it checks if there's any more vertices to search for. So while not PQ empty, and first gets the first priority item in the priority queue, and let's get the total weight of the path to that current node being searched. All right, and also we get the node that we're currently searching from, and then we check all the adjacent vertices with the adjacency list, and then we check we add the new total weight of the path if we go to this adjacent vertex. All right, and then we get the adjacent vertex as well. So to get the new total weight of this path, we just add the weight to our current location as well as the weight of the edge that leads to this adjacent vertex. All right, and then we just check, is the weight that we currently know of to this adjacent vertex greater than the weight if I take this new path? So if this path is going to be shorter than what we currently know of. If so, then we can change the distance to that future location to the new total weight, and then we add this path, since it adds into priority queue. So and we reassign the new cost, since that's now the cheapest cost now, and nothing can trump that cost, I guess. And using the following graph, so let's find the shortest path from one location to another using Dijkstras algorithm. So first, I imported queue, and I have the start location and an end location, and then the number of vertices in this graph. All right, and I created this adjacency list. All right, so in this adjacency list, I have it in a way so that the first value is the node that is adjacent to, and the second value is the cost, the weight of the edge that connects that adjacent vertex. All right, and then first I create the list that contains all the distances from the starting vertex, and I set the starting vertex distance as 0. All right, and I create the priority queue, and then I copy the same code from earlier where I checked if there's any more nodes to search from, and I get the highest priority item in the priority queue. I set the total weight to that location I get the total weight to that location with the current path from the start of the priority queue, from the start of the vertex of the path, I guess. And then I get the current node I'm searching from. And then I just do the normal thing where I check all the adjacent vertices. I get the new total path by adding that weight, and I get the adjacent vertex. And then from here, I just check is this current new path less than the distance I currently know of, and then I update it if it is, and I add it to the priority queue, and I get the distance at the end. If I run this, so I have this code here. If I run it, so the distance from 8 to 1, the shortest distance from 8 to 1 is has a distance of weight of 9. So from here, I can go from 8 to 1 would be cost of 9. Since, if I take 1, 3, then 6, that's going to be a cost of 10. That's not a possible path. If I go from 5, 1, 3, that's going to be 9. And that's how we get the shortest path, I guess. All right. Now, Bellman-Ford, on the other hand, another shortest path algorithm is Bellman-Ford's algorithm. Oh, before I go on to Bellman-Ford algorithm, does anyone have any questions about Dijkstra? No questions? All right. Now with Bellman-Ford algorithm, as opposed to the Dijkstras algorithm, Bellman-Ford involves something called dynamic programming, where it relies on the relaxation concept on all the edges, as opposed to with Dijkstra, where it just applies to the ones that it's currently searching for. It also starts from bottom up and stores values that will be used later down in order to determine the shortest path, starting with at most 0 edges and 1 edge, and so on and so forth. So I don't have to explain anything different. There's no new special structure with Bellman-Ford, so we can just jump straight into implementation. So to implement this algorithm, it's a bit different from all those different graph searching algorithms that we've seen so far. So instead, it will be much easier if we use an edge list. So other than that, like Dijkstra, we need to keep track of the distance between the start to every other vertex. And the implementation below will be used for a directed graph, since you need to keep track of it. You have to look at both directions, I guess. And however, to implement this for an undirected graph, you just need to include 2 if statements in the nested for loop going in the opposite direction. All right. So in here, I set the distance between each vertex to the start to some arbitrarily large number. It doesn't have to be the number here, as I said, and I also set the distance from the start to 0, since that's the key concept of one of the key concepts for shortest path algorithms is that starting and ending at the same place will always be 0. Now we loop through all number of vertices vertices minus 1 times, since the longest ever path that we'll ever have is v minus 1 vertices. So we loop through v minus 1 times, and we loop through all the edges. So we loop through, so we get and we get the starting vertex of the edge, so where the edge starts and where the edge leads to, and the weight of the edge. And we just check if we take this edge, if we take the weight of this edge from the start, and we just check if it's less than the ending vertex. So if we take this edge, if we take this edge, so we take the distance we know currently to this whatever ending from this the vertex that we start from the edge from, and we add its weight, and if we add this edge, that means it will lead us to this ending vertex, right? And if we check, if we take this edge and it's less than the current known, weight of current known distance to the ending vertex of the edge, then we know that if we take this edge, that means it's cheaper to get to this ending vertex. So we set the distance to the ending vertex as starting from the start vertex and adding the weight. Now we can do the exact opposite if it's an undirected graph. So if we go from the end to the start, then that means if we go in the opposite direction, it'll be cheaper as well. So if we do if this ending vertex plus weight is less than the starting vertex, then we can add the starting vertex, and that will determine whether or not, and that determines whether or not in the opposite direction, I guess. So using the same graph, from the Dijkstra example, we can run bellman-ford as well. So we can start from 3 to 6 and see the shortest path from 3 to 6. So here, if I run, run, it gives us 16. So from 3 to 6, it gives us the shortest path of 16. All right. Now, the last, so does anyone have questions about bellman-ford? No questions. All right. Lastly, we'll look at floyd-warshall. So the last algorithm that we'll look at today is an algorithm called floyd-warshall. So unlike the last two algorithms that we looked at, floyd-warshall looks at starting from every single vertex and ending at every single vertex. It's dynamic programming algorithm, so this breaks down into smaller sub-problems that combines them back together into a bigger problem. This is done by, finding the quickest path from a certain vertex to another vertex, all while taking some middle vertex and comparing that to the quickest path that we know so far. All right. So as I previously mentioned, the implementation is just comparing between the current path that we know so far, from starting from one location to ending in another location, or starting from one location, taking some middle path and ending at another location. So, and with floyd-warshall, it's best to be using an adjacency matrix since we need to keep track of all the distances from one location to another. And I will also include input into the adjacency matrix in this implementation. All right. So in this first question, I get input for the number of vertices in this graph, and and I get the number of edges in this graph. All right. And then I create an adjacency matrix. So with some arbitrarily large number as for each of the weights from one location to another, but also the set that I have to loop through and set starting and ending at the same position will be 0, since that's the key concept. All right. Now I loop through all the edges to get input. So I get input for the starting position, the end position, and then the weight in this input. And then I set the adjacency matrix from the start to end to equal the weight. And if it's undirected, so this should be undirected. If undirected, include the opposite direction. So adjacency matrix of end to start equals the weight. All right. Now we loop through all the vertices to go through in the path, and then we loop through the vertices that we start from, and then the vertices that we end from. All right. Now we just compare. Is taking the path through the middle of through this random vertex in between, is this going to be cheaper than through the currently known path? So we check from A to B, then to B to C. Is this cheaper than just going from A to C directly that we currently know of? And if so, then we just we set A to C equal to AB plus BC. All right, and that's going to be setting the cheapest path. All right, and note that the order. So you can have for C in range and for A in range first. The order doesn't matter, except that you always have to have the middle. You have to set the vertex that you're traveling through as the outermost loop, since that controls the size of the subroutine for dynamic programming. And then using the same graph, I can find all the shortest path from every start position to ending at every other position. So if I run this, it gives me all the path, all the distances from one location to another. All right, and that's with floyd-warshall. Now comparing between all these these path algorithms, so all of them have their own strengths and weaknesses with differing efficiencies. So in terms of Dijkstras algorithm, it's faster than bellman-ford, and bellman-ford is faster than floyd-warshall. With Dijkstra having an efficiency of v log e time, so v meaning the number of vertices and e meaning the number of edges, while bellman-ford has an efficiency of ve, and floyd-warshall has a time complexity of v cubed. All right. It's pretty simple to understand that floyd-warshall has an efficiency of v cubed since you're looping through v 3 times. And then with bellman-ford, you can see that you're looping v times and e times. So you're looping v, and then you're looping through all the edges. All right. Now, Dijkstras algorithm, being a greedy algorithm, will always seek to choose the smallest number possible, and as such, will break with negative edge weights. So you can't have any edges that have a negative weight. All right. Now, bellman-ford and floyd-warshall, on the other hand, can deal with negative edge weights. However, they will all three of the algorithms will break if there are something called negative cycles. Now, this is what happens when there's a cycle that in the graph where the sum of all the the weight of the edges results in a negative value. So let's say we start at some position and we take a loop around and we end up at the same location. You know, if we end up at the same location and we take all these edges and we end up with a negative value, that's going to be a negative cycle. So and that's not the fault of the algorithm if we have a negative cycle. Rather, it's the fault of the question, as you cannot determine the shortest path with a negative cycle. Since if you just keep looping around the cycle, you'll always end up with a smaller and smaller number, and that's going to be a shorter path. And in the end, you're going to end up with you're going to end up back at the same location with a shorter path. And as such, that also breaks the key concept of the shortest path algorithms, where if you start and end at the same location, you should always end up with 0. So if you end up with a number less than 0, that means there's a negative cycle, and as such, you can't find your shortest path. And with bellman-ford, we only need a loop v minus 1 times, because at most a path should only contain v minus 1 edges. All right. However, if we extend the loop to v times instead of v minus 1, we should end up with the same values as v minus 1 times. However, but with a negative cycle, it will give us a shorter path, and as such we'll end up with different values if we loop one more time, and that will detect a negative cycle. With floyd-warshall, on the other hand, going back to the second concept of shortest path, the shortest path starting and ending at the vertex will always be 0. However, when we introduce negative cycles, if we start at a vertex in a negative cycle, you'll end up with a negative number once you return to the same vertex, and as such, that breaks that concept. So if we loop through all the vertices and check the path starting and ending at itself, they should all be 0, unless there's a negative cycle in the question. And lastly, floyd-warshall is an all-pairs shortest path algorithm. So rather than having to loop through every single vertex and run Dijkstras algorithm or bellman-ford's algorithm, you can just run floyd-warshall's algorithm once and determine the shortest path between any two pair of vertices. And so you don't have to keep. Let's say we want to find all the shortest paths starting from every vertex and ending at every vertex. You can just run floyd-warshall once, as opposed to with Dijkstra you have to go through every single vertex, and in bellman-ford you have to run through every single vertex to find the shortest path. All right, and that concludes all the comparison analysis and all the shortest path algorithms. I'm only going to be assigning a few questions this week, but I do encourage you to try at least using all 3 algorithms for these questions. All right. Does anyone have questions about what I just taught so far? Any comments, concerns, anything? So if there's no questions, I expect you guys to be able to do all these questions here. Yes, no, anyone, hello? Have I been talking to myself the whole time?
I get it.
All right. I mean, I'm just wondering for feedback, just so that I don't want you guys to be swamped with all this knowledge. I guess with all this information. So no questions, I guess. All right. And if anyone does have questions, feel free to reach out to me. I'm pretty much available 24/7. So if anyone has questions about uh, anything we've taught so far, even going back to week 1 stuff. Like, if anyone has any questions, feel free to ask. But other than that, if no one has questions, then we can wrap it up here. So going once, going twice, going 3 times. All right, I guess that's it for today. Hope you guys have a wonderful day, and I hope to see you guys soon next week.